Hello guys, welcome back. Today we are diving into classic challenge in reinforcement learning, the Lunar Lander problem. If you have ever wondered how AI can land a spacecraft on moon, you are into the right place. In this video, we will build an AI agent that learns to safely land a lunar module on the moon surface. We will go step by step from understanding the problem to training the agent using cutting-edge reinforcement learning techniques. So get ready to see our AI agent face a tough journey from crashing on its first try to eventually mastering the art of land with style. So this is our lunar module, and our objective is to train the agent to land this module safely on the moon surface. The agent's actions are controlled by continuous state information, and it must balance fuel usage, control, and landing precision. Okay. So this is the environment information. We have action space of size 4, observation space of size 8, and this is the import. Okay. So this is a classic rocket trajectory optimization problem. According to Pontryagin maximum principle, it is optimal to fire the engine at a full throttle and turn it off. And that's the reason why environment has actions like engine on and off. Okay, now let's look at the action space. So we have four discrete actions, 0, 1, 2, 3. 0 is do nothing. That means no thrusters are fired. 1, fire left oriented engine. 2, fire main engine. And 3, fire right oriented engine. Okay. Next, let's look at the observation space. So the state is an 8-dimensional vector. Okay. So what are those 8 dimensions? The coordinates of lander in x and y, the linear velocities in x and y, its angle, its angular velocity, and two booleans that represent whether each leg in the contact with the ground or not. Next, rewards. So after every step, the reward is granted. So for example, the reward is increased or decreased the closer or further the lander is to the landing pad. Okay, so if you land closer to the landing pad, you'll get more reward. If you land further to the landing pad, the reward will be decreased. And reward is increased by 10 points for each leg that is in contact with the ground. And these are for the firing the side engines, main engines. The episode will receive additional reward of -100 or +100 points for crashing or landing safely, respectively. An episode is considered a solution if it scores at least 200 points. Okay. And episode termination. The episode finishes if the lander crashes, lander gets outside of viewport, or the lander is not awake. That means not moving. So let's get started. So for this problem, we are going to use Google Colab. You can use Jupyter Notebook or any other editor you would like to. So we'll start with installing the Gymnasium. So pip install. So I already have Gymnasium installed. If this is the first time for you, this will install the Gymnasium. Okay. Next, we will import. So import Gymnasium as gym. Let's have few more installs which are needed. So next one is Swig, and next we will install the Gymnasium box 2D. Okay, so the installation is completed. Next, we will have a few imports. Let's run that. And next we'll have the environment. So we can get the environment from here. Okay. Okay. Next we will have the state. So we dot observation space dot shape and the state size. So the shape and okay, and we have action size. Action space dot n. Let's print these. So we have state, print action size, state size, and print action size. So let's run this. Okay. Okay, so we have the state. So this is the shape. This is the state size 8, and this is the action size 4. Now let's have few hyperparameters. Okay, so these are our hyperparameters: learning rate, mini batch, gamma, replay buffer size, interpolation parameter, maximum number of episodes, max time steps in each episode, epsilon starting value, ending value, the decay value, and the scores on 100 episodes. So in this tutorial, I'm not going to go deep into these parameters. I have created a separate video where I've discussed these parameters in detail. I'll leave the link in the description. Please visit if needed. Okay, so let's run that. Next, we'll create the brain for the AI agent. So let's create ANN, artificial neural network, NN dot module. Next, we'll have the constructor. We'll call the super. Okay, so this will be action size. Let's have the seed as well. So seed 42 self dot. Okay, so we have 3 fully connected layers, 1, 2, and 3. And this is the input layer. This is the hidden layer. We'll have 64 neurons in each layer. And this is the output layer. Okay, so this looks good. Let's have the forward pass. So this forward pass takes the state, pass through first fully connected layer, apply the ReLU activation function, then pass through second fully connected layer, apply the same activation function, and then pass through third activation function to the output layer. Okay. I have created a separate video where I have discussed artificial neural network in detail. I leave the link of that video in description. Please visit if needed. Okay. So now let's run this. Okay. Next, we will work on the replay memory class. Now let's quickly brief about replay memory. So replay memory class is designed to manage the agent's memory of the game experiences. It stores the state, action, reward, next state, and whether the episode ended for each step in the game. So on the current state, agent will take an action. Based on the action, agent will be rewarded. Agent will land on the next state, and this done to notify whether this action has ended the current episode. So this entire tuple is called one experience. I have created a separate video where I have discussed in detail about replay memory. I'll leave the link in the description. Please visit if needed. Okay. So let's go back. Okay. So first we'll create a constructor, and this will take capacity. This will be the capacity of replay memory. So this is the memory and this is the capacity. Now let's have few functions. So first would be push. So self event. Event is nothing but experience, and this function is responsible to pushing the event into memory. So self dot memory dot append event. And we need to check if memory exceeds the capacity. If that happens, we need to remove the oldest experience from the memory. So if length of memory is greater than capacity, we'll remove the oldest experience. Okay. Now let's have a sample method. So this function is responsible for taking random experiences from the memory for the agent to train. So experiences. So this batch size is number of experiences. So let's say, for example, if the batch size is 100, then we'll randomly pick 100 experiences from the memory for the agent to train. Next, we will convert these experiences into PyTorch tensors. So what do we have in experiences? It's a tuple: state, action, reward, next state, and done. So first we'll get the state. So let's understand this. So in experiences, the first element is a state. So we have list of states. We V-stack them, convert them into PyTorch tensors, and then convert them to float. So, okay. So we have list of experiences. Okay. And for example, let's say these are the three experiences: state, action, reward, next state, and done. So first we'll extract these states. So we'll get the list of states. Then we'll V-stack them into one NumPy array. Then we convert them to PyTorch tensors because neural network operates only on tensors. And then we'll cast them to float. So again, we have created a separate video where we have discussed all of these things in detail. I'll leave the link in the description. Please visit if needed. Okay. So now let's create for state actions. Okay, now we have all the 5 elements. Actions can't be float values, so we'll change it to long. And the fifth element done is a Boolean value, so we'll convert it to integer. So as type. Okay, and at the end, we'll return states, actions, rewards, next states, and does. Now let's run that. Okay, so we have error, syntax error. Looks like we have extra bracket here. So let's remove that. Let's run it again. Okay, so we have another error. This should be delete. Okay, now let's run it again. Okay, so we are good. Next, we will work on the agent class. And this will take a state size and action size. So we have a state size and action size. Next, we'll create two networks, one for local and one for target. Okay, so let's call it as local queue network and target queue network. And we'll pass the state size and action size. So here is our network class. Okay, and this takes state size and action size. Okay, let's quickly understand why do we need two networks. So one local network and one target network. So it's a design choice in deep Q learning to improve stability and convergence of training. So local Q network, it updates actively and it is used to predict the Q values for the current state. Okay. And the target Q network, it used to compute the target Q values for the next state. And it updates less frequently than local Q network. So in this video, I'm not going to dig deep into this concept. I have created a separate video where I have discussed in detail that why do we need two networks, local versus target. I'll leave the link in the description. Please visit. Okay. So let's go back. Now next we need the optimizer. So we'll be using Atom Optimizer, and that will update the local network parameters. The learning rate we have defined here, and also we'll have replay memory initialized here. Okay. Okay. What is it complaining about? Okay. Okay. This should be torch, not touch. Okay. Next, we'll have the training step. So let's call it as T step, initialize to 0. Next, we'll have the step function. So step and self, and let's copy it from here. Okay. So this step function will be called by the agent after each action. Okay. So agent will pass the experience and we'll store this experience in memory. So self dot memory dot push, and we'll pass this as a tuple. So tuple. Now we don't want to train the agent after each step. Instead, we want it to get trained after few steps. So, now we'll make use of this T step. So the self dot T step, and if self dot T step is 0. So in order to train the agent, first we'll get the random experiences from the memory. So experiences dot mini batch, and our mini batch size is 150. So before we select these experiences from memory, we need to ensure that memory has at least these many experiences. Okay, so if next we'll call the learn method. So we have yet to implement this learn method. So this method will take experiences and the discount factor, that is gamma. So we have gamma here, so we'll pass that. Okay, so with that, our step function is ready. Next, we will have the get action function. So this method decides which action agent should take based on the current state. And it also handles the exploration and exploitation trade-offs. So let's quickly understand that. So, exploration exploitation trade-off is a fundamental concept in reinforcement learning that describes the balance between two comparing objectives. Okay, so exploration, the agent tries new actions to discover potentially better rewards or strategies. And exploitation, agent uses the knowledge it already has to maximize reward by choosing the best known action. And why this trade-off is important? Exploration is necessary to ensure that agent doesn't miss out a better option or strategies that hasn't tried yet. And exploitation ensures that agent leverages its current knowledge to achieve high rewards efficiently. So I have created a separate video where I have discussed in detail about exploration exploitation trade-off with an example. I leave the link of that video in the description. If this concept is new to you, please watch that video. Okay, so let's go back. So this get action function takes the state and epsilon value. First, we need to convert this state, which is in NumPy array, to PyTorch tensor. So state, so let's copy it from here. Okay, and here we don't have list, we have state dot unsqueeze. So we have a state, which is NumPy array. We convert it to PyTorch tensor using this function, then cast to float, and then unsqueeze 0. This is used to add a batch dimension since PyTorch models expect input in batches. Now put the local network in the evaluation mode. So eval. So we switch to evaluation mode to avoid unwanted updates. Next, state will be passed through network without calculating gradients for efficiency. Okay, so for that, what we'll do with torch dot no grad, and we'll get action values Okay, so we have the action values. Now, before we do anything, we'll put the network back to the training mode. So self dot local queue network dot train. Next, the exploitation trade-off. So if random dot random, so if generated random number is greater than current epsilon value, we'll pick the action from these action values. Okay, so these action values would be something like this. So these are predicted Q values for each action. So here we have 4 actions. So the size would be 4, action 0, action 1, action 2, and action 3. So we'll pick the action with the highest Q value, the best predicted action. Okay, and for that we'll do return np dot max, and we'll pass the action values. So action values dot cpu dot data dot numpy. So this is exploitation part. Now the exploration part. Else agent will pick the random move. So possible values are 0, 1, 2, and 3. Okay, so return. Okay, so this is responsible for selecting a random action from agent's action space when agent decides to explore rather than exploit. So action size, which is 4, and this function will produce the array with elements 0, 1, 2, and 3. So random choice will pick a random element from the array. And with that, we are done with the get action function. Next, we will implement the learn method, and this method will take experiences and gamma as parameters. So this learn method is used for training an AI agent in reinforcement learning. Okay. So before we proceed, let's understand the Bellman adaptation for deep Q learning. Bellman adaptation for deep Q learning. So we compute the target Q value using this Bellman equation. So this is the Q target, S and A. S stands for current state and A stands for action. R stands for the reward. This is gamma, the discount factor. This is the Q network. S prime is the new state, and then A is the action in the new state. So on the current state, agent takes an action A. On that action, agent receives the reward R, and then agent lands on the new state, S prime. Then again, on the new state, agent can take all the possible actions, and we will pick the action that gives the maximum reward. So this is in future, in the next state, multiplied by the discount factor, which determines how much importance is to give in the future reward. The gamma value lies between 0 and 1. We generally take the gamma value as 0.9. So again, on the current state S, agent takes an action A. For that, agent receives the reward R, and then agent lands on the new state S prime. On that new state, agent can take any of the possible actions. We will pick the action that gives the maximum reward multiplied by the discount factor, added to the reward. That becomes the targeted Q value for the current state. So this is on the target network. Now let's continue with the learn method. So first we'll unpack the experiences. Okay, so experiences has these 5 elements. Experiences. Okay, now we'll compute the target Q values. So let's call it as next Q targets, and this would be self dot. We'll use the target Q network. So target Q network. We'll pass the next states. So next states dot detach dot max, and then unsqueeze. Now let's understand what are we doing here. Okay, so this is the line. And first understand target queue network's next states. So we pass the batch of next states through the target queue network to get the queue values for all the possible actions. Okay, so we pass the next state to the target queue network. And the shape is batch size and number of actions. So batch size is number of experience samples and num actions is the total number of actions agent can take. We'll see that with an example in a moment. So let's proceed. So we have understood this part. Now the detach method. So target network is used for calculating the target queue values and we do not want to update its weight during backpropagation. So detach method removes the computation graph from tensors, stopping gradients from flowing through it. So this way we ensure that during backpropagation, we only update the local queue network, not the target queue network. Now the max function. So this function finds the maximum queue value for each next state across all possible actions. The Bellman equation selects the best possible future queue value, assuming the agent follows the optimal policy. Okay, so remember the Bellman equation. So on next state S prime, agent has all the possible actions available. Agent picks the action which has the maximum queue value. Okay, so let's clear the screen. So max of 1 operates on dimension 1, the action dimension. So max of 1 return two values, the maximum key value for each state and the index corresponding to the maximum key value. We don't need this. We only need the maximum key value. So we'll do max of 0. That is this one. Okay. Now let's understand the unsqueeze method. So this method adds a new dimension to the tensor. The expected shape of next queue target is this, but right now it's only the batch size. So this method makes it a column vector. Okay, so let's understand this with an example. So let's say these are the next state queue values. So here our batch size is 4. Okay, and these are the queue values for all actions in the next state. So we have 4 states, 1, 2, 3, 4, and these are the queue values. Okay, so this max function picks the maximum queue value in each state. So here it is 2.5, 4.2, 2.0, and 3.3. Okay, so this is what we have here. Then this unsqueeze method, it gets it to the correct shape to ensure it aligns with other tensors like rewards and duns. Okay, so let's go back to the code. So we have calculated next queue targets, that is this part, this right part. Okay, now let's use the Bellman equation. So queue target, so let's call it as queue target, and that is reward plus, so we have rewards plus. Okay, so we have next queue targets multiplied by gamma, that's the discount factor, this part, and then we multiply it with 1 minus duns. So why this 1 minus duns? So let's say if done is equal to 1, that means if the next state is terminal, then we'll just add the reward. This entire part will become 0. Okay, so we have calculated the queue target. Now we'll calculate the queue expected on the local network. So we have calculated this part, the queue target on the target network, and now we'll calculate the queue expected on the local network. So that is self.local network. We pass these states dot gather function 1 comma actions. So this selects only the queue values corresponding to the action taken. So we pass the next states to the target queue network to compute the target queue values and current states to the local queue network to compute the expected queue value. And now we will calculate the loss. So we'll use mean squared error functions to calculate the loss between predicted queue values and target queue values. So that is this part. Okay. Now we will reset the gradient. So optimizer. Okay. So we have initialized the optimizer here, and that is using the Adam optimizer. And here we reset the gradient from previous step to prevent accumulation. Okay. Now we'll compute the gradients of loss with respect to model parameters. So loss dot backward. So we back propagate the loss to the network, and then we will update the weights. So optimizer.step. So let's summarize this. We use mean squared error function to calculate the loss. Then we reset the gradient from the previous step. Then we back propagate the loss and updates the weight. Okay. And now we will update the target queue network using soft update method. So self dot soft update from here, and target queue network, comma, interpolation parameter. So we have interpolation parameter here. Next, we will implement the soft update method. But before that, let's understand about this soft update, okay? So we have a local model, the neural network actively learning. Then we have a target model, a more stable network. And we use something called interpolation parameter, a factor between 0 and 1 that controls the update speed. So we gradually update the target model, and that update speed is controlled by this interpolation parameter. So if the parameter is 1, the target model immediately copies the local model weights, that is hard update. And if you use a very small value, let's say 0.01, then the target model updates very slowly, blending in only 1% of the local model parameters at a time. And we are going to use 0.01 as the interpolation parameter value because we want our target model to updates very slowly. And this will be the equation we'll be using. So parameters of local network multiplied by interpolation parameter plus 1 minus interpolation parameter into parameters of target network. Here we can see if we take the value 1, then 1 minus 1. So this entire part will become 0, and the target would be equal to local. So that is the hard update. And if we take interpolation parameter as 0.01, then this is 0.01 times local plus 0.99 times target. So 99% of target parameters, 1% of local parameters. So we are blending in with only 1% of local model parameters. Now let's implement the soft update method. So soft update, and this takes these 3 parameters. Okay, so this is the soft update method. So interpolation parameter into local network parameters, this part, and 1 minus interpolation parameter into target network parameters. And we'll copy it to the target network. Okay, now we are done with the agent class. So let's run this. Okay, so we are good. And next we will initialize the agent. So agent, and we'll pass the state size, action size. So let's run this. So we have another issue in class init. Okay, so here we have a typo. Let's run this again. Let's run the agent again, and let's run this. Okay, another issue, learning rate is not defined. So we are using the learning rate here, and we have it here. Let's run that. And let's run the agent. Okay, so we are good. Now let's run the agent. So we have a number of episodes here. So for episode in, so at the beginning of each episode, the first thing we will do is reset the environment. Okay, so we'll call env dot reset. and this returns the initial state and the information. Okay, so let's check that. So go to environment and the reset. So the parameters, okay, so the reset returns the observation, the initial state, and information that we don't need. Okay, so we'll discard that. Now let's have the score 0. Now maximum time steps, so max time steps. Okay, so for ST in range, so first we'll get the action for the agent. So we'll call agent dot get action function, and we'll pass the state and epsilon value. So epsilon is not defined, so epsilon value would be, we'll start with 1. So epsilon value here, we'll say epsilon starting value. Okay, so now we have the action. Now we need to perform this action. Okay, so that is environment dot step, and we'll pass this action, and this will give us, let's check the step function. So this is the step function, and this gives the observation space, the next observation, that is the next state, reward, and terminated, so that is done, and two more values, truncated and information that we don't need. So it gives the next states, rewards, reward, done, and what else? Truncated and info. And okay, this is deprecated, so we don't need these. So we'll just discard that. Okay, okay, okay. So now we have next state, reward, and done. Now we will train the agent. We'll call this step function. Okay, so agent dot step, and this step function takes this. Okay, so we have state, that's a current state, action, reward, next state, and done. Okay, now the next state will become the current state. So state, next state. Okay, now let's update the score. So score, reward. Check if episode is done. If that's the case, we'll break from the current loop, current episode. Now we'll add the score to the queue we have created. So we'll add the score dot append score. And next we will update the epsilon value. So max of epsilon ending value. Okay, so we will start the epsilon value where it is. So we'll start with the epsilon value 1. The ending value is 0.01 and the decay rate is 995. Okay, so that's how we'll update the epsilon value. It will never go down below epsilon ending value, that is 0.01. Now let's print these scores. So we'll print after every 10 episodes. So if episode style 10 is equal to 0, we will print the number of episodes and average score after every 10 episodes. And if average score of last 100 episodes is greater than 200, that means we have solved the problem. Okay, okay, so let's check that. An episode is considered a solution if it scores at least 200 points. Okay, so let's run that. Okay, so we have an error. Module ANN is missing the required forward function. We have the forward pass method. Okay, indentation. Let's run it. Let's run this again. Let's run the agent again. Okay, another issue. So is not supported between instances of int and tuple. So let's check that. Okay, so we have memory, capacity, replay buffer size. Let's check that. Okay, so we have a problem here. Okay, now let's run it again. Okay, we did not run that, I guess. Okay, we have another issue. List object is not callable. Okay, there is an issue. So where are we calling that? Okay, so this should be sample. Okay, let's run it. And another issue, soft update. 3 positional arguments, but 4 were given. So where is the soft update? Okay, so this should be self. Let's run the agent again. Okay. Okay, now it's running without any issues. Okay, after 30 episodes, the average score is minus 192.24. Okay, after 100 episodes, the average score is minus 159. So we can clearly see that average score is improving. Okay, after 200 episodes, the average score is down to minus 97.58. After 250 episodes, the average score is minus 78. So that's good. It's increasing. So after episode 380, the first time average score is positive. So we have crossed 100 after 570 episodes. The average score is 110. After 730 episodes, the average score is 193. So we are very close to 200 now. Okay, so congratulations. After 738 episodes, we have crossed the benchmark of 200 with average score 202.88. Now, let's add the code and watch our AI agent successfully land the lunar module on the moon. So this piece of code will record the agent video and save it. We won't go into the details of the rendering code as our focus is on building and training the AI. Okay, so let's run this. Okay, so we have an issue. Okay, so there is an argument missing, epsilon. Okay, we'll pass 0.0 because our model is already trained. Okay, so now it's running. Okay, so we have a video now. Okay, it's looking good. It's looking good. Okay, it's close to landing. Almost there. Okay, so our AI agent has landed the lunar module successfully. Let's run it again to capture another video. Okay, this is looking much better than previous time. Okay, so lunar module is between two poles now. Okay, perfect landing. So we have missed a one thing here. We can save the model once the problem is solved. That means the average score of last 100 episodes is greater than 200. So we'll save the model using torch.save method, and we are saving with the name model.pth, and it will be saved in the same location along with the video file. So with that, we are done. Our AI agent has successfully landed on Moon thanks to reinforcement learning. I hope this breakdown of Lunar Lander problem and learning process behind it was helpful. If you have enjoyed the video, please like and subscribe to our channel. The full code of today's AI agent will be in the video description. So feel free to check it out and give it a try yourself. Thanks for watching. I'll see you in the next one. Bye bye. Take care.